Okay, hello. We are now going to discuss Chapter 12, Section 2, which deals with chi-squared two-way tests. So 12.1 dealt with a chi-squared goodness of fit, where you have one sample and you have one variable, and it has to be a categorical variable. The first thing to recognize as to when to do a chi-squared test is that the variable or variables has to be categorical. It's got to be with people. It's got to be something like their race or their religion or what state they're born in or their hair color, etc. Of course, if it was quantitative, it was things like their height or their weight, and in such a way that it hasn't been categorized, then it's going to be something else like a t-test or something. But anyway, and so we've got three kinds of chi-squared tests, and so I wanted to explain to you how to recognize the three kinds. And I think the main way is to sort of look at the sampling method and look at the terminology. So a chi-squared goodness of fit test, and that's section 1. And that is not an x squared, that is a chi-squared, that's the Greek letter chi. That is when, in essence, there is one sample, and one categorical variable. Okay, and there'll be these hypothesized values for the variable. It'll say it is thought that in this city 30% of people are Republican and 40% are Democrat, and then the rest are other. Okay, so there'd be just one sample and one variable. That's chi-squared goodness of fit. And so then we've got two others in this section. That's in 12.1. In 12.2 we have the chi-squared test of homogeneity. Chi-squared test of homogeneity of populations. Homogeneity of populations. And you can just call it the chi-squared test of homogeneity. But in this case, we are going to have more than one population. We're going to have two populations. And so the deal is we are going to have two samples. That's the way to recognize it. We'll have two different samples and one categorical variable. One categorical variable. And so what it'll say is, so the big word you're looking for here is, it'll ask the question, is there a difference? Is there a difference between the two populations, between the people of Alabama and the people of Mississippi in regards to a categorical variable, in regards to their religion or their political party affiliation? So, is there a difference? That's sort of the big word, and you notice there's two samples in regards to things. And then the other one is very similar to it, and it's the mechanics of it are done basically in an identical way. And that's a chi-squared test of association or independence. Chi-squared test of association or independence. You can just call it a chi-squared test of association. And in that one, we are just going to have one population and thus one sample, but it is going to be comparing two categorical variables. Two categorical variables. And what it'll say is there an association? So it'll say, is there an association between the two variables? So it'll say, we took this sample and we're asking, is there an association between, let's say, political party affiliation and race? Or let's say what state people were born in and their opinion on some issue, okay? And so, but you notice there's one sample and it asks, is there an association? Or another keyword, so that's a keyword you're looking for, is there a relationship? Is there a relationship between people's race and their political party affiliation? Has to be two categorical variables. Or it could ask, are they independent? Is political party affiliation independent of people's gender, let's say? Okay, so and so the key words I think you're looking for, the way to, first of all, it all has to be categorical variables, but look at the sampling method. It's one sample, one variable, goodness fit, section 1. And you'll put your data in a list. And in these two, we're going to put it in a matrix, which I'm fixing to show you. But, so there you go. So if you see the word, is there a difference in the populations? That's homogeneity of populations. And is there an association, relationship, or are they independent, or some synonym thereof? And you notice one sample and two variables. That's a chi-squared test of association, which is going to be our second example today. So that is your that is your little introduction. So let's look and let's do this problem. And let me say one other thing in regards to chi-squared. Chi-squared is always a test. Okay, it's always a test. And so how do you know they're asking you to do a test? Is that it may ask you to do a test. It'd say, hey, perform a test of significance. All right, or it may say, is there statistically significant evidence? Statistically significant evidence of something. And in general, when they ask, is there statistically significant evidence, that means do a test. And when you're dealing with categorical data, it means do a chi-squared. Now, we've had categorical data earlier in the year in regards to proportions. And we'll talk about that in another video. But anyway, but this is what we're doing today. So let's look at this particular problem. It says, a researcher wishes to see if there is a difference. That's one of our key words. Is there a difference in the male and female adults in her city in regards to their political party affiliation? Okay, all right, and so that's certainly categorical. She takes an SRS, certainly circle that, that's a big deal, of 60 males in the city and finds that 40 are Republican, 10 are Democrat, and 10 are other political affiliations. Takes another SRS, so we have two SRSs of 40 females and finds that 10 of them are Republican, 20 are Democrat, and 10 are other. Draw an appropriate graph, first of all, to compare the males and females and perform an appropriate test. So first of all, performing the appropriate test, you notice there's two samples. This is going to be a chi-square test of homogeneity of populations. But the first thing it says, draw an appropriate graph of this situation of categorical data. And so that's a chapter 1 problem. And hopefully you're seeing how in the world of AP stats, really sort of the whole year can be covered kind of in one problem or much of it. So that's a chapter 1 issue, and it could be questions about how the data was collected, like that's a chapter 4 issue, and then of course we're doing statistical inference, which in this case is chapter 12, and they could maybe fit in some sort of probability problem, which would be chapter 5 or chapter 6. But anyway, so draw an appropriate graph. And so what we'll do, you remember with categorical data, is the graph with categorical data is going to be a bar graph. And so what we need to do that, first of all, I'm going to make a little two-way table. Of course, it could ask you to do that. It could say make a two-way table with this data. And so I'll do that very thing. And so we'll say male and female, Republican, Democrat, and other. And so there's 40 male Republicans, there's 10 male Democrats, and there's 10 others. And so then we have 10 female Republicans, 20, and then 10, like that. Now, we need percents to do an accurate side-by-side bar graph, okay? Because we've got more males than females, and so that can kind of distort what we're looking at here. So we'll come up with the marginal distributions. And so there's a total of 60 males, and there's a total of 40 females, and there's a total of 50 Republicans, 30 Democrats, and 20 other. So there's a total of 100 people in our study. Now, in order to make a bar graph, I need the relative distributions. In other words, I need the percent of each. And you could go either way. You could say, well, I'll divide horizontally like this. I'll divide it by row, and that would tell me that of the 50 Republicans, 40 of them are male, or 80%. Okay, and then divide 10 by 50, and so of the 50 Republicans, it's 20% female. But I'm going to do it by column. To me, that's kind of more getting the issue. The issue here is there a difference in the males and females. So I'll divide them by column, and so I'll say for the males, so 40 divided by 60, that's 0.6 repeating. So that would be 2/3 of the males are Republican, and then 10 divided by 60, so that's 0.16 repeating. So roughly about 17% of the males are Democrats, and then the same thing with the other. 10 divided by 60, 0.16 repeating, like that. Okay, and then for the females, 10 divided by 40, so that would be 0.25 are Republican, and then 20 divided by 40 is 0.5, and then 10 divided by 40 is 0.25, so 25% of the females are other. And then we'll make our bar graph of these amounts. And so we'll just say, well, this is my percent over here on the vertical axis, and the biggest one goes up to 0.6 repeating, so I'll just go up to 70%. So I'll go 10, 20, 30, 40, 50, 60, 70. So 10, 30, 50, 70, let's say. And then down here, so my little key, what I'm going to say is I'm going to say the open bar is going to be male, and then the filled in one will be female, like that. And so then for the Republicans, I'll label this as political party. Always label your axes. So for the Republican, so for the males, they are 2/3, so it'd be 67%, like that. And then for the females, 0.25, so that's going to be about right there. So like that. And then we say for the Democrats, okay, for the male it's 17%, that's about like that. And so 50% for the female. And then lastly for the male, once again, that's going to be, 17% roughly, and for the females it goes up to 25%. So like that, and then there you go. And so that's how you make a side-by-side bar graph, and that allows you to easily see what's going on with the data. So you could look at that, and if you're asked to describe that, you would say, well, the males are much more likely to be Republican, whereas the females are much more likely to be Democrat or to be other. So, and that's all you'd have to say. I mean, if you're asked to describe quantitative data, you would cuss, and you describe its center, unusual, value, shape, and spread. You don't do that with categorical. You just make a bar graph and describe what you see. And so that's what we did in Chapter 1. And so now what we'll do is we notice certainly there does appear to be a difference, but what a hypothesis test will allow us to do, it allows us to be a bit more exact as far as, is there a statistically significant difference in the males and females? There certainly appears to be a difference here, but is it plausible that that difference is due to sampling variability? All right, and so that's what the test is going to do. So performing a test, you'd say it's categorical data. All right, we've got two populations comparing these this categorical variable of political party. So this is a test of homogeneity of populations, and just like every other test, we're going to have to follow our THAME acronym. We have to state the type of inference, state our hypotheses, our assumptions or conditions, then do our mechanics, and then state our ending, our conclusion in context. So first of all right, so we're going to do our test. So the first thing is a name, and this is a chi-square test of homogeneity of population. So you have to remember those names. Those names are not going to be in your calculator. You have to remember them. So the chi-square test of homogeneity. In other words, are these two populations the same when you look at them? All right, are they homogeneous? And so that's the first step. The next thing is our hypotheses. Now, so your hypotheses, your null hypothesis for a test of homogeneity is always going to be that there's no difference. Okay, I mean, remember in other hypothesis tests we've done, the null hypothesis is that there's no, when we did the two sample thing, that there's no difference in the two proportions, or there's no difference in the two means. Here's there's no difference between the two populations in regards to the categorical variable. So it's always going to be there's no difference between, and of course state the context, the males and females of this city in regards to the political party affiliation. The alternative is always going to be that there is a difference, okay? And then you can just use tally marks. All right, our conditions. Now you remember our conditions, otherwise known as our assumptions, it's sin, okay? But in regards to chi-squared, we don't have the n of normality. It's that our expected counts are at least 5. And so they're actually easier to check than other conditions that we've had, but they're basically the same as we had with the chi-square goodness of fit. So the first thing is it says that SRSs were taken, thus independent random conditions met. Remember, it's really ISIN because we have two samples. They had to be taken independently. In other words, one sample could not have been influencing the sample in any other way, or the occurrence of one sample couldn't be associated with a change in occurrence to the other sample. They just had to be done separately, independently, and that was certainly done here. So, and it's SRSs, not one of them, there's two of them, so that's how to do that. Our population sizes must be at least 10 times our sample sizes. So we have our sample size is 60 males and 40 females. So there is our independence condition. That is because we're using sampling without replacement. Now, if we were using sampling with replacement, okay? Or if we were doing a experimental situation here, where we did not have sampling at all in essence, all right, then you don't check this condition. But we had sampling without replacement from both populations, and so we have to say that, all right? And so then lastly, once again, we do not say the word normal in this chapter, okay? We don't have normality. Our distribution we're working with is called a chi-squared distribution. And our third condition, you just have to merely say that all the expected counts, and say what they are, okay, are at least 5, okay? And I'll show you how to find these expected counts in a second. Now, the result of this is that the distribution of our test statistic is going to follow a chi-squared distribution, which I'm going to explain more fully in another video. But this is all you have to say here. Okay, so it's really these conditions really in this chapter are kind of simpler than our other ones. Now we are going to do our mechanics, and I'm going to show you how to do this by hand. So we've got to list our chi-squared test statistic, our degrees of freedom, and our p-value, those 3 numbers. And yes, our calculator is going to have a shortcut to it, but you have to understand how to do this by hand. So we're going to calculate our chi-squared test statistic. Now, the chi-squared test statistic, if you go on your formula sheet, formula Strapey Stats, the bottom of the first page, there it is. The chi-squared, and that's not an x, call it a chi, is equal to the sum of all my observed values minus my expected values over the squared over the expected values. And so that's what I'm going to do. All right, and so let me show you how this is done by hand. And so what I need to do, once again, to find my chi-squared test statistic, it is equal to the sum of my observed values minus my expected values squared over my expected. All right, so I'm going to write down my little matrix. Those are my observed values. So from my sample, we have males and we have females, okay? And we've got Republican, we've got Democrat, and we've got other. My observed values, I've got 40 male Republicans and 10 female Republicans, and then I've got 10 and 10, and then I've got 20, and then I've got 10. Okay, now those are my observed values. So in the formula for each cell, I'm going to do there. Now, how do you find the expected values? Our little formula for expected values is this. Now, in the first section, for goodness of fit, the expected values, you just multiply your given proportions times your total sample size. But here's our little formula for expected value in regards to section 2 with the 2A table. It is going to be the row total, and so you're going to have to memorize this. This is not in your formula sheet. The row total times the column total, the row total times the column total over the table total. Over the table total. It's a bit tedious, but let me show you what that means. So I've got to get my column totals and my row totals. So we will get our marginal distributions in order to do this. So I add these up, so I have a total of 60 males. Add these up, I got a total of 40 females. Then I've got a total of 50 Republicans. I've got a total of 30 Democrats and 20 other. So my table total is 100. Now, I want you to think about this. All right, what does the term expected count mean? The expected count means this is how many we would expect to have in our sample for each cell if the null was true. And remember, our null hypothesis is that the males and females are exactly the same in regards to political party. Well, think about the political party here. In our whole group of 100 people, half of them, 50 out of 100, are Republican. So if the null is true, and if there's no difference in the males and females, we're expecting half of the males and half of the females to be Republican, if the null was true. Because we got 50 out of 100 in our total here over on their side. So if the null is true, and 50% of the people are Republican, I'm expecting 50% of the males to be Republican, and 50% times 0.6 is going to be 30. That is the expected number of males that are going to be Republican if the null is true. And similarly with females, I'm expecting 50% of the females to be Republican. So that'd be 0.5 times 40, or that would be 20. Similarly for the Democrats, in the total group, I've got 30 out of 100 that are Democrats. So if the null is true and there's no difference in males and females, I'm expecting 30% of the males and 30% of the females to be Democrats. So I would say 60 times 30%, or 60 times 0.3, and that is 18. Similarly with the females, I'm expecting 30% of them to be Democrats, and so that's going to be 0.3 times 4, and so that's going to be 12. And then for the others, I'm expecting 20%. In the total population, 20% of the people are other political party affiliations. So if the null is true, I'm expecting 20% of these 60 to be other, and so that'd be 0.2 times 6, and that's 12. And then 20% of the females, that'd be 0.2 times 40, and that's 8. Okay, and so those are my expected values. And think about what I just did there. For this cell, for every one of the cells, for this cell, what is the expected count? It is the row total, which is that, times the column total over the table total. Okay, and then so I did that for every cell. So for female Democrats, to find the expected count, I just said 30, the row total, times the column total, 40, divided by 100. Now, similarly, that reasoning, you could look at it the other way. You could look at it using, in essence, our column total here. You could say, well, in this whole group of 100 people, I've got 60% of them are males. So therefore, within each political party, I should expect 60% males and 40% females. So we've got 50 Republicans. It should happen that 60% of them are male, if the null is true. And so that would be 0.6 times 50, which is 30, And you say, well, in regards to females, I'm expecting 40% of them to be female. And so that would be 0.4 times 50. And in regards to the Democrats, it should be 60% males and 40% females, and so forth. So that is sort of the theory behind it. And so you've got to memorize, in essence, that formula. And so now we are going to find our chi-square test statistic by using our little formula here. All right, and so what this means is I'm going to take every cell, and I'm going to take its observed value, subtract its expected, square it, and divide it by its expected. So to find the chi-square test statistic for each cell, I'm going to take the observed value, 40 in this case, minus 30, squared divided by expected 30. So this is a bit tedious, all right? And then plus, this means add them up. That summation means add them up. And I'll go for the female Republicans. So that would be 10 minus 20 squared over 20. Now for the male Democrats. And so that is going to be 10 minus 18 squared over 18. And then plus, now for the female Democrats, 20 minus 12 squared over 12. And now for the male and other, so it'll be 10 minus 12 squared over 12, and then plus, and then 10 minus 8 squared over 8. When you add all of those up, it's equal to 18.05 repeating. And then, anyway, but the actual numbers are actually, it's important to be able to find these actual numbers. So 40 minus 30 squared over 30, that's 3.3 repeating. And then this cell is 10 minus 20 squared, which would be, so that's going to be negative 10 squared, which is 100, divided by 20, which is 5. And so for this one, that's going to be negative 8 squared divided by 18, which is 64 divided by 18, which is 3.5 repeating. And then for this cell, it is 5.3 repeating. And for this one, it's 0.3 repeating and plus 0.5. And like I said, that's equal to 18.05 repeating. That is our test statistic. And that's how you find it by hand. Now, by the way, so each of these things are what is known as the components of chi-squared. And you have to be able to find those. All right. So, and we're going to do a follow-up analysis. We're going to look back and we're going to say, well, which cell contributes the most? And we look and we say, this one does. That's the biggest of these numbers, and that corresponds to the female Democrats. So the female Democrats are the most different, in essence. They're contributing the most to the chi-squared. And the fact that that number's the most, it means it has the biggest relative difference to its expected. Okay, the ones that are really close, like this 0.3 repeating, that means 10, 10, it wasn't that different from 12. So in regards to the two other ones here, they aren't that different. All right, so now how do we find, now we need the degrees of freedom. The degrees of freedom identify which chi-squared distribution you're working with, okay? Similarly, what we talked about in section 1. Here's the formula, another formula you have to memorize. It's not on your formula sheet. It always is going to equal to the number of rows minus 1 times the number of columns minus 1. Number of columns minus 1. And so in this case, our rows, we have 3 rows. So we say minus 1, and then the number of columns, columns go up and down, so they're like columns on a building, so we have 2 columns, so it's 2 minus 1, and so that's going to be 2 times 1, and so that's 2. So, the chi-squared distribution is a very skewed to the right distribution, but the more degrees of freedom, the less skewed it is. But so we've got 2 of our numbers. Now we got to find our p-value, and so we have our chi-squared test statistic is equal to 18.05 repeating. So we've got that. We have our degrees of freedom is equal to 2. Now, how do we find our p-value? Of course, now on your formula sheet, so on your tables, this is the last of our tables. Okay, we have, there it is. Like I said, this is table C, chi-squared critical values, and so it's a very right-skewed distribution. And so because it is squared, a chi-squared value is always positive. So Z and T, half of them are negative. Chi-squared is always positive. And so your p-value is always going to be the probability of that or more unusual. So it's always going to be to the right of your value, always going to be a greater than. And so what you would do using this table is you would say, okay, my degrees of freedom is 2. So that's telling me I'm using this chi-squared distribution. I'm using this row right here, okay? And by the way, as you go down here, so the more degrees of freedom you have, the less right skewed it is. So like a degrees of freedom of 1 is like insanely right skewed. But anyway, and you would go as close as you can to find, say, our chi-squared is 18.05, and so these values here are all chi-squared values, and when you go looking for 18.5, it is off the table. Okay, so it is off the table. The biggest one we have is 15.2. So we know that our p-value is actually going to be less than 0.0005. And so anyway, and so on this, if you're just using your table, you would say the p-value is less than 0.0005. In other words, it's going to be statistically significant at basically any reasonable value for alpha. Now, how can you find using your calculator? Well, if you're given your test statistic and you got to find a p-value, you can use a CDF function, in this case chi-squared CDF. Just like when you're given a z-test statistic, you could use normal CDF. When you're given a t-test statistic, you could use t-CDF to find a p-value. In this case, chi-squared CDF. So we're going to use chi-squared CDF, and it's always going to be that value and bigger. Okay, that value and bigger. So there's my lower bound. My upper bound is infinity. So you'll always, and then you just put your degrees of freedom is equal to 2. So that would be showing your work there. And let me remind you where this is. Okay, so we're going to go second distribution, just like we're going to normal CDF or t-CDF. There it is, chi-squared CDF. We'll never use chi-squared PDF, by the way. So this would be chi-squared cumulative density function. And so we hit enter. Our lower value 18.055556, let's say. Upper value is infinity, so we'll just hit 9 trillion or something, and our degrees of freedom is 2, and it gives us there 1.20 times 10 to the negative 4th. So I'll just say our p-value is approximately equal to 1.20 times 10 to the negative 4th. In other words, it's going to be 0.00030 is 120. So that is our p-value. Okay, and that's how you do that. And now our p-value statement is the same as it's always been. This p-value is below 0.05, so we reject the null. We have convincing evidence that, and then you restate the alternative. Yeah, where did my alternative send? So we have convincing evidence that there is a difference. Okay, so between that. So just to finish off our little test here. So you would say, So you have to write down these three numbers, your chi-square test statistic, your degrees of freedom, your p-value, and then your p-value statement. Hopefully you've gotten used to by now. This p-value is less than 0.05, so I reject a null. There is convincing evidence that there is a difference in the males and females in this city in regards to political party affiliation. And that's not surprising when you go back and you look at our when you look at this. When you look at this, you're like, whoa, there appears to be a difference, between the males and females, and that's what that p-value is telling us as well. That's what that p-value is telling us. Okay, and then the last thing you'll be asked to do is follow-up analysis. So when it asks you to do a follow-up analysis, what it's asking you to do, it is in essence asking you to look at your components of chi-squared and say which ones are contributing the most. Which ones are contributing the most? And when you look at this, you would say, and like I mentioned before, so each of these numbers comes from each of these cells. And you look at the biggest ones, our two biggest ones are these. And that corresponded to the female Republicans and to the female Democrats. Those are those two cells. And so you would look and you'd say, well, the two biggest ones are the female Republicans and the female Democrats. They're contributing the most, whereas the smallest one would be this one. And so that corresponds to the male others. So the male others are contributing to the least. So the way you would word your follow-up analysis is you would just say the female Republicans and the female Democrats contribute the most to the chi-square test statistic, whereas the male other contributes to the least. So you just kind of say what's contributing the most and what's contributing the least. Okay, that's how you do it. Let me show you the shortcut with your calculator. Okay, yes, you need to understand how to do that formula and how to find your components and to do it by hand. But once you understand that, you can do this quickly with your calculator. And so this is what we're going to do. With the chi-squared two-way test, with the test of homogeneity, or what we're fixing to do, the test of association and independence, we are going to go to a matrix. Okay? In other words, when we're given a two-way table, okay, most of the time, so you've got a two-way table and you're asked to do inference with it, we're going to enter this into a matrix. All right, and the way you enter it to a matrix, there's the matrix menu. So this is the first time we've really used matrices this year, I think. And so it's right there. So you're going to go second and hit x to the -1, which is matrix. Second matrix like that. Then you're going to go to edit. All right, you'll go to edit. So you're going to hit your arrow button and you're going to go edit. And I always put the observed in matrix A. Okay, that's what I always do. So put the observed in matrix A. And so this is 3 by 2. So I just hit 3, enter, and 2, enter. Okay, and if you didn't enter that right, then your matrix wouldn't appear correct. And then I just enter these values. So I've got 40, and then enter, and then 10, enter, 10, enter, 20, enter, 10, enter, 10, enter. And so I believe I entered that right. And so now that I've entered that to a matrix, I'll quit out of that. So I go second, quit. Then I go to stat, test, and you scroll down to chi-square test. Okay, that. Now, chi-square goodness of fit, that's section 12.1. That's not this. We're doing a chi-square test, otherwise known as a chi-square two-way test. Okay, so I hit enter. So my observed, I just put them in matrix A. Now, if it didn't say matrix A there, say it just said nothing or whatever, the way you can put matrix A there is just go second matrix and then just hit enter on the name of A and it'll put A. It's going to automatically calculate your expected values. Okay, for you, which is really nice. Okay, so and I just always have it store them in matrix B. Now, if you're doing a goodness fit test, you'd have to find the expected values and put them on list too. But it's going to do this automatically. So we go calculate, and there it is. There's the three numbers that you have to write down in your mechanics. So that's all you have to write down in your mechanics is those three numbers. Okay, but you have to, like I said, you got to be able to find it by hand, and then you have to write down, you remember you always have to write down your expected values, all right, for in your conditions or your assumptions. You have to write them down, okay? The way you can easily find them now, by doing that chi-squared test, it automatically calculated them and put them in matrix B. So I'm just going to look at matrix B. So I'm going to go second matrix. I think the easiest way to do it is just go to edit matrix B. So I'll go edit and then matrix B, and there they are. There's the expected counts. Okay, you have to be able to find them by hand, but there you go. Now, And by the way, most of the time your expected counts are going to be decimals, and don't round them to the nearest integer. Okay? Do not do that. They'll count off for that. So you can round to like the nearest hundredths place or something, or just write them just exactly as they appear there. That's how you do a chi-square test of homogeneity of populations. Okay, let's look at our context too. Now our next problem is going to be done in a very similar way. So this one's going to go a lot faster because the mechanics of the chi-square test of association and independence are going to be exactly the same. The only thing that's different in association and independence is the terminology that is associated with it, and in essence the sampling method. Okay, those are the only, but everything else is pretty much exactly the same. All right, so let's look at this context. It says that an educational administrator wishes to see if there's a relationship, that's sort of a key word there, between how advanced the student is and his or her opinion about whether or not the school should have stricter discipline policies. He takes a random sample, that's a big deal to us, of the 99 of the students and gets the results shown below. Perform an appropriate test. Or another way it could word this, it could say, is there statistically significant evidence of a relationship between how advanced the student is and their opinion about discipline? And so, in other words, we need a p-value. And so you notice this, we've got two categorical variables and one sample. And so remember, where's my little sheet? All right, when you've got two samples and one categorical variable, that's homogeneity, which is what we just did. Now we have one sample with two categorical variables. Just one sample with two variables, okay? So, this is what we call a test of association independence. So we're going to perform our test, and so here we go. We got to do our little FAME acronym. We got to state the type of inference, and so here we go. So this is called a chi-square test of association or a chi-square test of independence. Okay. And once again, and the other thing is the keyword of relationship. When you see that keyword of relationship, that is telling you, association independence. That's one of the keywords. If it had said, is there a difference? Is there a difference? That's a good chance homogeneity. And once again, obviously by the sampling method, you can tell. So this is a chi-square test of independence. All right, so that is that. Now, the null hypothesis is always going to be that there's no relationship between the two variables, or that there's no correlation, or that there's no association between the two variables. And make sure to say what the two variables are. Okay? In this case, there's no relationship between how advanced the student is and their opinion on stricter discipline at this school. The alternative is always going to be that there is a relationship between the two variables, or that there is an association, that there is a correlation. Or the other way of wording this is to use the word independence. The null hypothesis would be that the two variables are independent. That you would say the null hypothesis would be that how advanced the student is and their opinion on stricter discipline at the school are independent. And the alternative would be that they are not independent. Okay? So I tend to use relationship or whatever's asked for in the problem. All right, so that's our T, that's our hypotheses. Now we have our assumptions, otherwise known as our conditions. All right, and it is, once again, we have to have randomness. It says a random sample was taken, so random conditions met. All right, we are using sampling without replacement here, so our population size has at least 10 times our sample size. You would not check this if they weren't using sampling without replacement. In other words, if it was an experiment where they did not use random sampling, okay? Or, anyway, but in this case, our population size has to be at least 10 times our sample size, so we would say that. And then what's the other condition with chi-squared? It's just that all the expected counts have to be at least 5. And I got those off my calculator. I'm not going to go through and do all that by hand again like I did a minute ago, where you calculate, all of this, and where the expected value is the row total times column total over the table total, all that sort of thing. But that's how you would do it by hand. And I'll remind you how to do it with a calculator again in a second. So that is that. And so then your mechanics, okay, and so it ends up being, there's my chi-square test statistic, my degrees of freedom, and my p-value. Okay, so let me once again remind you how to do this with your calculator. All right, so what we'll do to get our mechanics, we're going to enter this matrix into our matrix menu. And so we will go, matrix is right there, right above the x and the -1 right there. So I will go second matrix, okay? And so then I will go to edit, like that. And then this is 3 by 2, 3 by 2, like that. And so there we go. And so now I will just enter in these numbers. And so we got 12 and 16, 12 and 16 and 27 and 21 and 14 and 9, like that. And so I've entered those in properly, I do believe. 12, 16, yes I have. So now we'll do our chi-square test. So we'll do stat, we'll do test, and we'll scroll down till we get to our chi-squared test. There it is, right there. Observed is in A, it's going to store the expected in B, and I go calculate, and so boom, and there is what I have to write down in mechanics. So that is how I got those numbers there. Have to write those 3 numbers down. Now, by the way, so once again, these expected values, how did I easily access them? Well, they were stored in matrix B. So if I go second matrix, and scroll over to edit, and then go edit matrix B, there's those numbers. There's the expected counts. So if the null was true, this is how much we're expecting to be in each cell. And so the premise is, how different are these two matrices? They're obviously going to be at least different because of sampling variability. But when you look at them, are they really that different? You know, proportionally? And the answer that our p-value is telling us, no, they're really not that different. It's plausible that this difference is due to sampling variability. So therefore, the null is plausibly true. But anyway, and so our conclusion is this. Okay, so it's the same p-value conclusion we've been doing for several chapters now. All right, this p-value is greater than 0.05. All right, so I do not reject the null. There is not convincing evidence that, and then you restate the alternative in context. So there is not convincing evidence that there is a relationship between the two variables. In other words, there's not convincing evidence that there is a relationship between how advanced the student is and their opinion about stricter discipline at this school. And so there you go. That is how you do a chi-square test. Of course, and it could ask for follow-up analysis, and you do exactly what you did in that last problem where you talk about how much each cell contributes to the chi-squared. But that's it. Thank you for watching the video, and I hope you have a fantastic day, and I wish you much success. And in regards to chi-squared, please send me any questions you have about anything.